Okay, so today we're going to start with the scalars and vectors. We're going to start with the very brief intro of scalars and what does that mean, for example. So when we define it, we say that a magnitude or a value is good enough or sufficient to understand it completely. But for a vector, we need a magnitude and a direction for its complete understanding. So let's discuss this with an example. We say that, let's say, time is a scalar. When we make the statement, what do we mean by that? So, for example, if someone says that 40 seconds have passed by, let's say, or let's say 3 hours have gone by, or let's say 2 hours ago, or any reference to time, we are not required to add direction with this information. We don't say that 40 seconds upwards or 40 seconds downwards or left or right. We don't need to add this information. This value along with its unit is its complete information. That is why we will say the time is scalar. On the other hand, if we were to talk about, let's say, vectors, we would need to give more than one piece of information. So, for example, let's say if we talk about weight, now weight is a force, and force needs to have a direction. And by this time, we are very familiar that weight actually always acts perpendicularly downwards towards the surface of that planet or that massive object, right? When we say perpendicularly downwards, it means that it makes an angle of 90 degrees with the surface of that planet or the object, right? So if somebody says that the weight, let's say, of an object is 20 newtons, then 20 newtons is its magnitude that we generally refer to as that vectors need magnitude plus direction for the complete understanding, and scalars only need magnitude, right? So this was the magnitude of time, which is a scalar, without the information of direction. And this was a magnitude of weight or force, which we know that the direction is downwards. So we had a magnitude and a direction for its complete understanding what weight is. Similarly, just to discuss one more example, let's say if we talk about mass. Now, mass is represented as in kgs, right? So when we say that, let's say we have an object of 3 kgs, we don't add the information that it is 3 kg downwards, upwards, left, or right, right? So the information of direction is not required for its complete understanding. The value along with its unit is already encapsulating its complete understanding what this value means or what the value of this mass may look like in real life or in real terms. But on the other hand, if we talk about weight again in comparison to mass, we need to know or we must suggest the direction in which that direction of force will be acting. Let's take one more step further. Let's say we talk about velocity or acceleration or a force. Uh, Again, not only the magnitude, but the direction of that value or that quantity will also be required for its complete understanding or its complete message to be delivered. So this is just a basic understanding of scalars and vectors. The main lesson or the main idea behind this video would be about vectors and vector addition, right? Okay, so let's discuss vectors and what is a vector and what does it represent and how to visualize it. If you can get good at visualization, then the question itself does not become or does not pose any problem to the person or to the student who's trying to solve the question. So let's look at it from this way. So vector, in particularly vectors, we will be looking at all types of vectors. For example, ranging from displacement, we have velocity as opposed to speed in scalars. We have acceleration. We have force, right? So something like this, right? Let's talk about force, as this is the easiest one to visualize when understanding vectors. Now let's say that we have an object that is placed on the floor like this, and a force acts on it in this direction, let's say of 50 newtons. Now I know because of this action of force, this object will slide along if it overcomes the friction. It will slide along and quite possibly will be visible to me after a few seconds at this location because we applied this force. It could just be sliding pulse, or the force could be continuously applied to it. But the reason, or at the end of the day, what we are observing is that the arrow represents the direction of motion or the direction of application of force on this object, right? So we know that it's going to go towards the right side according to this frame of reference. Okay. Similarly, if we have an object, let's say this on another situation, and if a force is applied towards the left side, how do I know that it is on the left side? We're observing the arrow. So always pay importance or pay heed to the direction of the arrow itself. This is which is going to tell you that where this object wants to go or is experiencing a force in that particular direction. So similarly, if let's say we have an object at this place and we place an arrow like this, so even if there is no magnitude represented, we still know that there is a force that is trying to make sure that the object goes towards the upwards direction, right? Let's say this force could be 30 newtons, right? It could be greater than or less than the weight of the object. So if it's greater than that, it would be lifted. If it is less than that, it won't be lifted, right? Okay, so now we understand that the arrows have an importance. And for a vector that is represented with the arrow, this part of that vector is known as the head, and this part is known as the tail. Why we're introducing this vocabulary? Because there are a few methods to solve vector addition or vector resolution that they involve these terminologies. So we must be familiar with that. Let's try to look at a different example. Let's say that if we had an object like this, and there is a force acting towards the right side, and there is a force acting towards the upward side. How do we understand or how do we visualize what's going to happen to this object? There are multiple ways. Some students can figure it out very directly or very easily that the object is going to be moving towards this direction because of the action of both vectors. Now, for other students who are facing difficulty to understand this, what you can do is you can implement or you can think about these two vectors one by one, right? So what you can do is, let's call this vector 1, let's call this vector 2. First, think about what's going to happen to the object if only vector 1 had acted on it. And then once you've taken care of that, you can move towards vector 2. What would happen to that object once vector 1 has acted on it and now vector 2 also acts on it? So an easier way to visualize this would be to just let's just move the box towards that side, right? So if v1 was acting, so the object might be at this location after some time, right? Now, once we've taken care of V1, now we will be acting or we will be implementing the action of V2. Now, V2 is going to make sure that the object moves in this direction. So after both of these two forces are done acting on it, I can understand or I can visualize or I can see that the object will end up at this location. So this is its end of journey, right? This is where it was starting from, and this is where it's ending. Now, counterintuitively, the other side is also correct. For example, if the vectors are still in this direction, so this was V1 and this was V2. A student wants to implement the force of V2 first. Doesn't matter, the outcome will still be the same. Now, first the object moves to this direction, and then after we've taken care of V1, now we have to involve V1. So the object moves towards this direction because of V1. So the final destination of this object will be in this location. By the end of the day, you realize that if this is our starting point and this is our ending point, the final resultant or the result of the two forces is still exactly the same as the first example. So it doesn't matter how you visualize it. What matters is that you can understand where the ultimate goal or what will be the ultimate direction if all these forces V1 and V2 had acted on the object, where would it eventually go because of both forces, right? Now, what we have done so far, the thing that we've just learned or tried to visualize is known as the resultant force. Now, always keep in mind that resultant is just a simple English language word that actually tells you the effect of combined forces. So the effect of combined forces, right? So we had V1 and V2. What are they going to do to this object? Simple question. So they're going to make sure that the object moves through this trajectory and eventually ends up here, right? Okay. Now let's try to implement this idea into a question, P1 question. So he tells you that there are two vectors represented over here. He's asking you about the resultant of the two forces. Now, of course, this is a P1 question. You can't draw this on your notebook because if this had been a P2 question, then we would have to use graphical methods that are in your course, right? But right now we can't do that. We will have to calculate this or at least visualize this with reference to some mathematical technique or some guesswork or some educated guess, something like that. Now let's see how this question may have gone about. Let's move away from this question and see what are the different implementations of this question. So there is a very simple method to figure out how to, what could be the range of my answers. So if these are two forces, let's say 3 newtons, I have two forces at my disposal, and 4 newtons. I can do three things with these two forces. First, I can find out the maximum resultant. And how can I do that? Now, this is your job to understand. I can produce a maximum of 7 newtons of resultant if both forces are acted in the same direction. Since they're both in the same direction, they're helping each other. So the combined effect would be 3 plus 4 making 7 newtons. This is the maximum, absolute maximum that these two forces can do, not more than this. Then I look for the minimum effect that these two forces can have. So what can be done? One of the forces it's towards the right side and one of the forces maybe on the left side. The other way around is also true. 3 newtons could be here and 4 newtons could be here. Doesn't matter. The final result would be similar, that there is only a resultant of 1 newton. Now, if it was the case in this one, then this would be in this direction, in the direction of the dominating force. If we were discussing this one, then of course 4 Newton is greater, so we would have a 1 Newton backwards, right? So this is the absolute minimum answer. So my resultant under these circumstances for these two, vector 1 and vector 2, my resultant will be always less than or equal to 7 Newton, the absolute best that they could have done, and it will be always greater than 1 Newton, the absolute minimum that they could have done for me. In all the other implementations, my answer should be between these two ranges, right? Let's look at it, what we mean by the ranges. Okay, so we were experiencing in the same direction, we experienced them in the opposite direction. Now let's experience them in a different angle. Let's say that they were acting at an angle of 90 degrees with each other. Now, I am absolutely sure that my answer will be between 1 Newton and 7 Newton. It cannot be greater than 7, it cannot be less than 1, right? So it will be between these two answers, right? Now, since I know that 1 Newton can only be possible in the minimum situation and 7 Newton can only be possible in the maximum situation, I'm going to cancel out these options and I'm not going to think about them. Now, let's try to think for this option. Let's try to observe how can we solve it. Now we know that the expected direction of this resultant will be in this direction. How? Because we've learned how to visualize it, how to understand what the direction, what the vectors represent, and where the object will end up, right? So is going to be somewhere along here. Now I realize that if I include the action of V1 and V2, we end up with a triangle that looks like this. So let's say this is my V1 and this is V2. Let's say this is 4 newtons and let's say this is 3 newtons. And this is my starting point and this is my ending point. So my object eventually moves in this direction, and very conveniently I can see that there is an angle of 90 degrees between these two vectors, right? So what I can do is I can use the Pythagoras theorem to find it out. So my resultant square, which is the hypotenuse most definitely, is equal to 4 square plus 3 square, and when I take the under root by cancelling this square over here, I get the answer of 5 newtons. Now, since all the answers in physics are supposed to be in two significant figures, you will see that all these answers are in two significant figures, not decimal places, but significant figures. So C is my answer for the current situation. And the idea that we've used actually originates from this point. This is option A, and this is option B. You could have taken any route to solve this question. You could have gone to V1 and then V2, or you could have gone to V2 and then V1. So the method that we're employing over here right now, or the visualization that we're using right now, in terms of physics syllabus and understanding, it's called head to tail connection, right? So what we've done effectively is that if this was our question, this is one vector, this is vector number 2. What I've done is I've removed this vector from this place and connected its tail to the head of another vector. So now I'm replacing this vector towards this place like this. So I can remove this vector because I've replaced it with the head to tail rule. So one tail is connected to the head of the other, and it has the next head over there, right? So the result of this would be from your starting point where you began the question to the ending point where you're ending it. So this will be your resultant, right? We will explore head to tail method again. We will explore arcing methods. We will explore parallelograms as well. But for now, this is what we have in mind, right? Okay, so this is how we solve a graphical question, or at least a question on MCQs uh, as a minimum, right? Let's look at this. This is does not require you to find out the value, but this requires you to visualize what's going to happen to the object that is placed over here. Now, first, let's dismantle the question that if a force is acting in this direction, the object wants to go in this direction, and if there is a force over here, the object wants to go downwards, right? But the combined effect of both forces leads us to believe that since the object is actually going to go, let's consider the same rule that we applied before, the head to tail method, right? So first the object moves to this location because of the influence of 25 newtons. Then the object has to go downwards due to the influence of 40 newtons, right? So the object goes downwards and ends up at this location. So that means, and let's try to do it from the other way as well. So first the object moves towards the 40 Newton direction and then moves to this direction because of the 25 Newton, because we have to include the effect of both vectors. And even from this side, the object ends up in the same location, right? So effectively, our resultant would be from the starting point to the ending point. That means that the object is actually going to experience a resultant in this direction. Notice that I put double arrows for resultant. That is how you indicate to the examiner that this is your final answer. These single arrows are the questions. Double arrows for P2 will be representing the resultant. So this is the final resultant direction, and most closely related option to this option is option B, right? So one more thing, it is impossible that the option moves or the object moves in the direction of the question. So 25 and 40, these are effectively option A and option C. If there are more than one force, if 40 Newton was alone over here, then most definitely C would have been the answer. If 25 was alone, then most definitely that would have been the answer. But since there are two forces and more than two, it's not possible, or in most cases, it's not possible that the question or the object actually moves in the direction of one of them. So if they're closely related, I will show another example, which is an extreme case in which it is possible that it may move eventually in that direction. So A was impossible, C was impossible, but let's talk about D. Another trick over here is that if you have any two vectors in any sort of direction or dimensions, you will always find the final resultant to be between them like this, on the side of the smaller angle. Now I understand that when I say between, it is very much, it can be taken as over here or it can be taken as over here. When we say between, it would always be meaning towards the smaller angle. So this is a smaller angle in comparison to the other one. So the resultant of these two vectors could be anywhere between these two vectors. It is impossible for this vector or for this answer to be outside of the question or on the longer or the larger angle of the side. It is impossible. This is not possible. This is possible. So when they represent option D, that is impossible because the resultant was supposed to be on the smaller side angle. Anywhere, it could have been anywhere, right? So the best guess right now would be option B, right? One extreme case in which this could have gone in the direction of the question is that, for example, if we had a vector like this, that is 400,000, let's say a very large value, and there is a vector upwards that is a very small, let's say 1 Newton. You can very clearly see that if you draw it with reference to the head to tail method, the 1 Newton vector will be very, very small in comparison to the 40,000. And if you apply Pythagoras theorem, you'll realize that this will be 3,999 something, which effectively cancels out the significance of this 1 Newton. So it looks like it gives the impression that it would eventually be moving in the direction of 40,000 Newton. But given long enough space, that 1 Newton would also become significant in comparison to 40,000, as it would definitely deviate it away from the main target with some angle. This is a bit advanced. No need to worry about that. We can just fixate on these ideas, right? Let's move towards this question and try to understand how the examiner can trick us into the vector addition or vector questions. Now, he says, again, the question is about 3 newtons or 4 newton act at right angles, which mean that the question is going to look like this. It could be like this. It could be like this. It could be in any configuration of as represented over here, right? And all these directions are with reference to the grid, which is north, east, south, and west, right? Because they have an angle of 90 degrees amongst each other. Okay. So it says that which diagram actually shows this. Now let's see what's the problem. What's the problem with option A? The resultant is shown by double arrows. That is correct, right? But if I had placed an object over here, it should have experienced, because of this arrow and because of this arrow, it should have experienced a resultant in this direction, because the combined effect would lead this object to this option. So in option A, they've drawn it incorrectly. Let's explore option B again, right? So if the object had been placed over here, because of 3 Newton, the object would be here. And then because of 4 Newton, the object will go somewhere along here. So the ending point of the object will be this side. So the resultant should have been in this direction. Again, option B is incorrect. Option A is incorrect. Let's consider option C. So option C looks promising. First, the object goes to this side. Again, there is no compulsion. You can start with 3 Newtons as well. Goes to this side, then 4 Newtons, makes it to go there, and then 3 Newtons makes it to come over here. So our starting and ending points are in the same direction as our expected direction. So option C is the best answer. Let's talk about option D. What's up with option D? Now, sometimes he says that choose an option in which the resultant is zero. When he says that the resultant is zero, then option D will be the answer. But let's see how that is. You see, because of these two vectors, 3 newtons or 4 newtons, your final resultant actually looks like this, right? So let's say this is our 5 newtons, because we solved the same question over here. We know that 3 newtons and 4 newtons at 90 degrees produce 5 newtons of resultant. And this is one of the common questions. So this is our resultant. So let's forget about the vectors given in the question. This is our final answer, right? But let's observe what the examiner has given us. The examiner says a direction, or mentions the direction opposite to that resultant that we would get. So this is what the examiner shows. 5 newtons or a resultant in the opposite direction. You see, we know that in simple terms that if we had equal forces on both sides, the resultant force is zero. There is no one dominating the object right now. There is no extra surplus force present that can dominate or that can dictate or that can decide what happens to this object. No one is greater than the other. All of them, or all the forces, are equal. They are balanced. Hence, there is going to be no establishment of any dominance of any of the two forces. So in this case, since both forces are equal and exactly opposite to each other at 180 degrees, the eventual resultant or the final answer of this situation would be zero. So what's actually happening is that because of 3 newtons and 4 newtons, the green 5 newton resultant exists. But since the examiner has added another resultant that is opposite to this one, it is going to cancel it out completely. So this is our zero resultant uh, diagram, right? If the question was show zero resultant, then D option would have been the answer. Another shortcut of zero resultant is the loop rule. Now, this loop rule is only for zero resultant cases, or only for such questions, right? You could have figured it out very easily. If the diagram completes a rule with the arrows, completes the loop with the arrows, then the resultant is automatically zero. Pick any side. You can start from this point, or this point. There should be a complete loop like this. Now I can see that if we move from this side, we follow the arrow of blue side, then we follow the arrow of the double arrows, and we come back to the same point we started from. Now this loop is being completed. That means that the resultant of this diagram would be zero. If you were to look at option C, let's recreate option C over here. We replace 3 newtons over here, or counterintuitively, you could have replaced this vector over here, right? Now, if you try to complete the loop rule in any manner possible, you could start from this point, you follow the black arrow, you follow the red arrow, but as soon as you encounter this junction, you face resistance from this arrow, which is the resultant. So in this case, the loop rule fails. That means that in this diagram, the resultant is not 0. This is just a trick to figure it out, but otherwise the basic theory actually is already explained in the questions, right? Okay, let's talk about this in terms of P2. How to draw the same question in terms of P2. So what he's going to do is going to give you a statement and is going to mention that, let's say that there is 500 meters displacement due north. And by the way, please be advised, since we are talking about vector addition, it's very possible that it could be any of these options. It could be talking about displacement, it could be given in terms of velocity, acceleration, or force. You should not be confused about it. So right now we are discussing the question in terms of, since it is meters, we are talking about displacement. Why? Because there is a direction mentioned. So this is not a distance, this is a displacement. So there is a magnitude and a direction. So complete information, this is a vector quantity. Similarly, then he says that the object moves, let's say 300 meters due east. Now, before you start the question, just visualize it, how this is going to look like to you. So if this is our grid, north, so what's going to happen that the object actually moved towards the north, right? I'm just displacing it a bit on the side, whether actually it's going to be like this. And then he moves 300 meters towards east, right? So this was its starting point and this is its ending point. The question he asks is, find the displacement. Now we know by the definition of displacement that displacement is the shortest distance between 2 points in a straight line. It doesn't matter. It's not going to take into account the road network. It doesn't care about anything else. All it cares about is moving in a straight line from start to finish. Just imagine that you're on a helicopter. You don't have to follow the roads. You don't have to follow any rules. You can just go from starting point to the ending point if you were sitting in a helicopter. So if you were standing at this point, you can go straight to this point without caring about the roads, rules, and anything else. So this green line would be your displacement from your starting to ending point, right? Now this is my resultant. This is the whole question, what it should look like by the end of the day. Now, first step would be, of course, you cannot draw 500 meters. 500 meters is half a kilometer. You cannot draw this on your notebook. You can't do that, right? So what we do is we need an intermediate scale that's going to shrink this diagram onto my piece of paper. It's going to make it small enough so that I can draw it over there. So I have to choose an appropriate scale that enables me to do that, right? And a small trick of for these questions is that your largest vector should be smaller, should be less than 10 centimeters. Choose a scale in such a way that your largest vector is less than 10 centimeters according to your scale. What do we mean by that? So the largest vector in my question is 500 meters. So I choose 500 meters as my starting point, or as the value that I'm going to refer to design my scale. So I need to make sure that 500 meters, when I represent it on my notebook, should be less than 10 centimeters. So the scale I choose will be 100 meters. In real life, right? Ratio, my notebook will be representing 1 centimeter. So if I draw 1 centimeter on my notebook, it would be representing 100 meters in real life, right? Okay, so if this is 500 meters, then most definitely it's very easy to see that it's going to be 5 centimeters. And if I have 300 meters, then it would be 3 centimeters. Now, once we've done that, we're going to draw this on our notebooks. And I know that there's an angle of 90 degrees between them. So first, let's draw the grid properly with angles, lead pencil, and rulers. Then draw 5 centimeters of north. I'm drawing it on a side, but in reality, it's supposed to be over here. So this is 5 centimeters, but I will write down 500 meters due north. Why? Because the question suggests 500 meters. I am adding a scale for my convenience. Otherwise, that's not how the question is. The question is in meters. Then I add 300 meters to the right. It's your choice. Because he says that first he does this, then he does this. Your object is standing at this point, then ends up at this location. Or what you could have done, a more simpler term, is to draw 300 meters due east like this, right? In both scenarios, in both circumstances, your final answer will not change. It will still be in the same direction as before or as explained before, right? Okay, so now this is where you're standing right now. So you have to find the displacement. So that would be your starting point, and this is your ending point. Please be advised, all of this is being drawn with the ruler, right? I don't have it right now with me. That's why the lines are a bit shaky. But please be advised that all of this has to be done with a ruler, pencil, rubber eraser, right? And so on and so forth. That is how you're going to draw this. Okay. Now, just simply place your ruler like this. This is your ruler. And draw a straight line from your starting point to your ending point, and then measure it. For the sake of example, I say that this measurement that you do comes out as, let's say, 4.2 centimeters. This is what you have measured on your notebook. But what you're doing is you're just trying to shrink the question from real life onto your notebook, right? So now we have to go back. We have to go back to reality where the units were in meters, right? So I will go back to the scale that I've selected, 100 meters to 1 centimeter, and convert this into reality, right? Or the real units of the question. So I know that 100 meters were representing 1 centimeter. So my 4.2 centimeter would be representing how much? So you can cross multiply or you can just calculate it mentally. This would come out as 420 meters, right? So this is a hypothetical situation. What you can do is you should solve this on your notebook and find out the correct and accurate answer, right? So my final resultant of this question would be 420 meters. Now, since displacement is a vector, I have given the magnitude successfully of the question. But what about the second part of my question? That is the direction. Where is the direction, right? So to find the direction, what you do is staying on the grid. I'm going to draw that again. Without the question, stay on the grid. This is your resultant, right? Stay on the grid and then place a D over here. You only need to measure just one angle, but for the sake of understanding, I'm going to solve it for both questions, both angles. Let's say this is angle X degrees and this is Y degrees. For the sake of example, let's give them values. Let's say this comes out as 65 degrees and this comes out as 25 degrees, right? Okay, right? And this is your resultant of 420 meters. Now, how do you mention the direction? What do you say or what do you write down for that? So we have north and east. We need to have them over here. So if a student chooses 65 degrees as its final direction, so what he's going to write down is that the direction will be 65 degrees east of north. So move 65 degrees towards east from north, and you will reach that vector. Or the other way around, the student could have used 25 degrees, so he would mention move 25 degrees north of east, right? So move from this point 25 degrees towards north from east. That is the direction. So the final answer of this student would be that the resultant is 420 meters, and for the sake of discussion, I'm choosing the 65. There is no compulsion. You could have written this down with 25 as well. 65 degrees east of north. This will be your final answer for your P2 question. And even if so, it comes in P1.